What I want to do now is talk about the t distribution, which is very related to and similar to a standard normal distribution. When I say the t distribution, it's actually a whole family of very similar distributions which are parameterized or characterized by a new number that we call degrees of freedom. So if we start with a standard normal distribution, which we recall, you recall we used to refer to as a z, as a special type of standard normal, a normal that has a mean of 0 and a standard deviation of 1. The t distribution is very similar to the standard normal, except it'll have a shorter peak and fatter tails. Something else about the t distribution is that it has this new value that I said, the degrees of freedom. And the degrees of freedom more or less are measuring how close the t distribution is to the standard normal. A standard normal that has 4 or 5 degrees of freedom will look more like this. And then as the degrees of freedom gets closer to maybe 30, and then if it has 200 degrees of freedom, it starts to look very, very close to the standard normal. So a t distribution is getting sort of taller and taller and taller, and the tails are getting thinner and thinner and thinner, approaching a standard normal distribution as degrees of freedom gets larger and larger. So just to quickly review, z is equal to any normal random variable, and then we subtract the mean, and then divide by the standard deviation of that normal random variable. If it's just a normal random variable x, it would be the standard deviation of x. If it's the estimator for the true mean, x bar, we subtract its mean and divide by the standard deviation of x bar, which is sigma over the square root of n. This is talking about a normal random variable x, and this is talking about a normal random variable x bar, which is the sample mean from a large population. Again, there's two different standard deviations. There's the standard deviation of the random variable x, and there's the standard deviation of the estimator for the true mean mu. Later when you take your statistics class, there'll be about 20 standard deviations. So the idea is the same, but there's lots of variables, and each one has its own standard deviation, and sometimes they're related. In this case, the variability of my estimator is related to the variability of the population itself. The thing that, I'll put this up here, standard normal x bar minus the mean over sigma over the square root of n. The trick with this formula is that it works beautifully in theory. The theory is actually quite elegant and mathematically awesome if you're a nerd. But in practice it's pretty useless, because if I don't know the true mean, I usually don't know the true standard deviation either. And so knowing that this is following a normal distribution is pretty useless in practice. So what we do sometimes is we take x bar, subtract the mean, and divide by s over the square root of n. Now s is our estimate of the real standard deviation that we got from the sample. It's the sample standard deviation. And so it's a pretty good estimator. The problem is that the chance of something going a little bit wrong is greater because my estimate is imprecise. It's not perfect. So that means the chance of getting an extreme result are going to be greater because I don't know as much about what I'm saying, because I'm using a estimator instead of the actual parameter. And that added uncertainty, that added lack of information about what's going on, but because we're estimating what's going on, means that this is going to be slightly less precise with more probability of something happening in the extremes, which is, of course, precisely a t-distribution. So the t-distribution is going to be exactly like the standard normal. We take an estimator minus the mean divided by the standard deviation of the estimator as estimated by S. Whew, that's hard to say. So we use t instead, and again, t will have a certain number of degrees of freedom, and that's determined by the sample size, n minus 1. So if you have 100 data points, you have 99 degrees of freedom. If you have 50 data points in your sample, you have 49 degrees of freedom. To calculate this, you can use a crazy formula and some integral calculus, or you can use this thing called Excel. Excel has two functions that we're really interested in. And t inverse. A t-distribution function and a t-inverse function are strangely designed to do hypothesis testing, which you do in your Decision Sciences 34 course, but they're not at all analogous to the norm dist and norm inv function, which is awful. So the t-dist function asks for 3 inputs. It'll be x, and then it'll be the next input we have is the degrees of freedom, and then lastly, it'll want to know whether you want to look at the area that's to the right in the tail, or the area that would be in both tails if you had information going out in both directions. So this will be the number of tails that you want to compute the area for. Usually, to make it similar to what we did with a norm dist function, we'll look at one tail. This tells you the area, and this will make life just awful for you. The norm dist function tells you the area to the left. The t-dist function tells you the area to the right. So if I give you some value x for a certain t-distribution, which is characterized by the degrees of freedom, and if you tell Excel one tail, it'll compute this probability, the probability of being greater than x. The t-inv function is also quite weird.